All right, so let's play with some numbers. So hit pause, and if you are so inclined, maybe team up with a friend and calculate these quantities for all 4 of these samples. So you're going to have a total of 16 numbers. The sum of the hydronium hydroxide concentration, their quotient, their difference, and their product. So hit pause and work through that. And through the magic of time lapse, you should get something like this. Again, keeping sig fig rules, and so the idea was that does something jump out at you? And something should, namely, that these guys are all the same. So the product is constant across all these solutions, but the other quantities, the sum, the quotient, and the differences aren't. And you might ask yourself, what's up with that? And here we go. So water is amphoteric. So that word means that it can be an acid or a base, basically depending on what's around. And this is true in general. Acid or base behavior is kind of a relative thing. But water is in the middle and is actually quite happy acting as an acid or a base, again, depending on what else is around. But here's the interesting thing. What if there's nothing else around? It can still act as an acid and a base. Just not one particular molecule doing both. So this is a thing. So water can transfer a proton to another water molecule. And what is the result of that? Well, you get a hydronium ion, so this is the water that accepted the proton, and what is left from the water that gave a proton is a hydroxide ion. The way to do this, and this is something you should be able to do if you're looking at what happens when you accept a proton. The formula changes, the hydrogen count goes up by 1, and the charge goes up by 1. For the thing that gave or donated the proton, the formula loses a hydrogen and also becomes negative by 1 unit. Now, what is the equilibrium constant expression for this? Well, it's just H3O plus times the concentration of OH minus. Now remember that the waters here don't go into this expression because they are pure liquids. And this particular equilibrium is deemed also highly, highly important, that it gets its own subscript, in this case Kw. And its numerical value at 25 degrees Celsius happens to be experimentally measured to be 1 times 10 to the negative 14. Again, at 25 degrees Celsius. This is called the autoionization constant for water because, again, the water is kind of proton transferring to itself. And just for yucks, let's ask ourselves, is pure water, acidic, basic, or neutral? Just from this. And, well, what do you think? Look at the stoichiometry. Well, if you look at the stoichiometry, assuming that the hydronium and hydroxide only come from this process, they're formed in a 1-to-1 ratio, which means their concentration is going to be equal, which means pure water, by definition, is neutral. So next question, can we calculate what that equilibrium concentration of hydronium and hydroxide is in pure water? And the answer is, of course we can. All right, so this ends up being a pretty straightforward equilibrium problem. We'll get the easy stuff off the bat. No waters. So we start off with no hydronium and hydroxide, and because of that, we can assume some forward progress to make at least a little bit, giving us X molar hydronium and X molar hydroxide. And so we know that Kw is going to be equal to the concentration of hydronium times the concentration of hydroxide. That equals X squared, which numerically equals 1 times 10 to the negative 14. To the negative 7. So the equilibrium concentration of both of these is going to be 1 times 10 to the negative 7. A couple of things. So this is the only concentration so these are the only concentrations where those two can be equal. The other thing, and this is probably the most profound one, profound enough that I think I'm going to give it in a different color here. These two concentrations are dependent of each other. They are not independent of each other because their product always has to equal 1 times 10 to the negative 14. And since their product is the same, if one goes up, the other one has to go down and vice versa. And that using this relationship right here, if you're given the concentration of one of these species in an aqueous solution, you know the other one. And this is a very powerful tool and one you'll be expected to use from here on out in like example problems.